relations, right? You have a relation between two variables. One is independent, can be changed freely. The other one will be changed accordingly. Either one, if you have an explicit formula, you know x is changed, y will be also changed. This one, even though it is not a very explicit, but you know if x is changed, y has to be also changed. So that's why I'm saying this is also a function, right? So a function basically is just the relation between two variables, how the change in each one of them are related, right? So here, taking the differentiation is just about the rate of change. The formula says dy over dx is equal to minus fx fy. So this is our amazing formula right here. Again, I have a couple of remarks to make. Do you still remember our notation for f sub x? F sub x. This is just what does this mean? This is just a partial derivative, right? So I said this is a partial derivative with different notations. This is partial f partial x, partial f partial y. Okay, so these are just notations for partial f partial x. The denominator is partial f partial y. But very, very importantly here, I have a minus sign coming right here. Okay, so dy over dx will be equal to minus partial x partial y. And in your pre-calculus class or any algebra class, one thing people have to be corrected is you cannot cancel terms freely, right? So if I'm looking at this formula in an incorrect way, not very correctly, I can see partial f can be canceled. I'm getting a partial y over partial x. But I have to warn you, that is not correct because you have a minus sign in front of it, right? You have a minus sign in front of it. And this is nothing, this is not talking about a portion, right? This is just a notation about partial derivatives. You cannot cancel this partial f with partial f, okay? One thing you learn in mathematics, number one, is you cannot cancel freely as you wish. So now I want to give you a proof of implicit differentiation. So this is exactly implicit differentiation. Again, in this class, we're not required to do proofs, okay? But this one is so nice, I still want to show it to you. So this is a proof. So I know x is changing, y is also changing accordingly. So essentially, I want to write y as a function of x, all right? So here, x is my independent variable. Y is a function of x. It's equal to 0, all right? So this is essentially to say what I mean by x is the variable, y will change accordingly. And then I want to take the partial derivative with respect to x on both sides. Okay? I'm going to take the partial derivative of x on both sides. The right-hand side is always going to be 0. No matter you're taking regular derivative or partial derivatives, hitting on constant function is always going to vanish. Right? So the right-hand side is always equal to 0. So I want to take a partial x on both sides. So the right-hand side is equal to 0. The left-hand side is going to be a partial f partial x. So this is the application of the chain rule. So bear with me closely here. Using the chain rule, the principle is I need to hit on the new variables for each one of them, right? The intermediate variables for each one of them. So x and y are my intermediate variables. So essentially, I have this chain. So f depends on x and y. These two will depend on x. So this is my chain. Are you with me? So this is my chain. So I want to take the partial derivative of capital F with respect to x. I need to go through x, I need to go through y, and end up with x again. Yes? Mm-hmm. So partial f, partial x, and then I need to take derivative dx, dx. But dx over dx is just 1. You're not canceling this again. We're not canceling. We're just looking at the derivative of a function f with respect to x. So that's why this guy is equal to 1. And the second one, I take a derivative with respect to f, and then dy over dx is equal to 0. All right? And then you want to solve for this unknown. And this is what we want to know, dy over dx. You can move terms around and do a division on both sides. So dy over dx multiplied by partial f partial y right here is equal to minus partial f partial x. That's why dy over dx is equal to minus f sub x divided by f sub y. This is exactly the formula coming from the chain rule. Okay? So this is a very, very useful formula for implicit function theory. Implicit function, you see this from everywhere. In fact, all the functions you see, only a very limited number of them you can solve them. Very, very limited, right? If I give you a function, unless it is a quadratic equation or some simple linear function, or some cubic function with a special form, you'll be able to solve it. Other than that, all the other functions is not easily solvable, right? Some of them are even unsolvable. But regardless, we can still do the derivative. So I'm looking at this function, and I want to compute dy over dx. Okay, dy over dx. Remember, you have a minus sign come from the implicit function theory. Okay, so to remind you to not forget about this minus sign, before doing any partial derivatives, just get a minus sign in front of it. Okay, and then the numerator is going to be f with respect to x. So f with respect to x, what do you have? Cosine xy multiplied by y plus pi y squared derivative with respect to x will just vanish. So I'm getting a minus 1 in the numerator. Okay, the denominator is going to be x cosine xy, then plus 2 pi y. Minus x will disappear. So this will be the partial derivative. So minus y cosine xy minus 1 divided by x cosine xy plus 2 pi y. So one last remark about the implicit function theorem is, even though we can compute the partial derivative or derivative here, we cannot ask for more. What I mean here is, usually if you compute the derivative of y with respect to x, you want to write down your answer in terms of x. All right? You want to write down your answer with respect to x because x is the independent variable. However, because we're using the implicit differentiation here, we cannot eliminate the variable y directly. So we have to live with it. So y will appear in our differentiation here. Okay? So I will compute one more implicit function theory, and then I'll give you a demonstration of partial derivatives. So let's say if I have 8 sine 2xy is equal to 5. I want to take the derivative dy dx. Okay, dy dx. So strictly speaking, if you want to use the implicit differentiation, you want to have a capital function f, which is equal to 0. Right? Here, you don't have a function explicitly yet, but you can just subtract both sides by 5 and make f xy to be equal to 8 sine 2xy minus 5. Okay, so you can simply modify your equation to move all the terms on one side of the equation. Okay, and then we can take the derivative with respect to capital F right here. Again, minus sign in front of it. Okay, minus sign, then f of x, then f of y. Okay, so what is your f of x?
8 cosine 2xy.
It's going to be 16y cosine 2xy. All right, divided by minus sign 16x cosine 2x1. Yes? So if I'm taking derivative with respect to y, x becomes a constant. This is really f. Now I can remove common factors, okay? Mathematical term of canceling terms. So it's going to be minus y divided by x in the end. Okay? So this is a derivative. For this function, you can solve for y. You can solve for y and take the derivative. So this function, if I want to solve for y, so sine of 2xy is equal to 5 divided by 8, and 2xy is equal to arc sine 5 divided by 8. So y is actually equal to 1 divided by 2x arc sine 5 divided by 8. So you can solve explicitly the dependence between y and x. And then we can compute the derivative of this kind of trig function, right? There are formulas of derivatives of arc sine function. You can take the derivative for this kind of functions. But without even solving for all the things, you can solve for here. Okay? What is even amazing is here. Listen be carefully. I can solve for y by just remembering arc sine function is the inverse function of sine function, right? I can plug in this implicit differentiation of y to eliminate this y variable to get implicitly what I have. So this is essentially going to be equal to minus 1 over 2x squared arc sine 5 divided by 8. So in the end, I get the answer depending on x only. Are you with me? Throughout the whole process, I don't need to take differentiation with respect to arc sine function at all. For a lot of you, you might know how to take the derivative for sine, cosine, tangent, and going on cotangent, secant, and cosecant function. For arc sine function, you might already forget the formula of how to take the derivative. However, I only need to solve and get an arc sine, and using the implicit function theory, I'm getting the answer without even taking the derivative of arc sine function, right? So this is a pretty useful way to get around some functions. The derivative is just too hard to compute. Yep.
Is the arc sine 5/8, is that exponential?
Arc sine function is not really exponential. It's just
Is it the exponent?
Yeah.
Or?
I take my words back. No, you don't have to know arc sine function. It's just constant. I'm sorry. I take my words off. I'm sorry, I made a mistake here. You don't even need to know the arc sine function, even if you are taking the derivative at this function directly. Okay, I'm sorry, you don't have to know the derivative here. Okay, I saw you have a variable appearing here. Okay, but you don't. Okay, so since we have a couple of short lectures, seems like your expectation is getting higher. Every time we have to finish earlier. That's not our usual norm. I want to generalize my implicit differentiation theorem a little bit, not too much. Okay? So again, if I have a function f x, y, z is equal to 0. Okay? So if you have 3 variables, x, y are the independent variables, z is the dependent variable. Again, this is not explicit. It's not in the form of z equals f x, y, where you can take the partial derivatives. But still, you should be convinced x, y are changing, z has to be changed. In other words, if we have 3 variables, 1 equation to govern them, only 2 can be chosen firmly. The other one has to be determined. Okay? So z can be regarded as a dependent variable of x and y. So if this is true, the implicit differentiation says I can compute a partial z, partial x, and a partial z, partial y without solving for z as well. Again, you have a minus on here, so it's going to be f of x divided by f of z. This is equal to minus fx divided by f of z. F of y divided by z. So the implicit differentiation works for partial derivative as well. Okay? So these are the 2 formulas for partial z, partial x. I can give you this very simple practice. Prove this. or if you are too scared of the word proof, show this. Okay, you can show these two formulas by exactly the same principle over there. Okay, you can take the derivative with respect to x on both sides, and you're going to use the chain rule. X, Y, Z are the intermediate variable. X is the new variable here. Right? You can get a formula coming out of the chain rule, and then you'll be able to get this formula. You take the partial derivative with respect to y, you're getting this formula. So you can actually show this. So very last, let's practice one example and we're done. X, Y, Z plus 6x plus 6z minus 2y is equal to 0. Okay. This function, you can indeed solve for z and compute the partial derivative directly for the function you got. But let's just practice our partial z, partial x. So this is going to be minus f of x divided by f of z. So we can simply denote this whole left-hand side of the equation to be our capital F. Okay. So what is f sub x? Y z plus 6. And f of z is equal to xy plus 6. Okay, so this is our partial z, partial x. And partial z, partial y is equal to minus fy f z. So what do we have? Minus x z minus 2 divided by xy plus 6. Again, a couple of remarks I want to make before I let you go. First remark is, you look at these final formulas, still, originally you want to have this partial derivative to be with respect of x and y alone. This x, y are the independent variable. But if you're using implicit differentiation, you have to live with the variable z appearing into your answer. Okay, so z is appearing in your answer. Second remark is all about learning mathematics. One way I want to convince you is mathematics sometimes is useful. Okay, sometimes you might find it completely useless. I agree with you. But second point, you want to learn mathematics. They are so much fun, right?